first one they did. So it kind of makes sense that they had a lower pass rate. Same data, except viewed from a compliance angle. So when you do that, the percentage of applications that meet acceptable risk levels decreases significantly. So these charts show compliance rates against the OWASP top 10 from 2007, and the CWB SANS top 25 from 2009. So both of those lists are a little bit outdated, but this like I said, this data is going back about 18 months. So evaluating against evaluating against those criteria, the pass rates are a lot lower. And the reason for that is that there's no risk built into the formula here. The application is considered to be not acceptable if it has even one flaw relevant to that taxonomy. And that's the way a lot of acceptance criteria work. If I've got acceptance criteria in my organization that says this application will not launch if it has any flaws in the OWASP top 10, one flaw is going to stop it from launching. So that's kind of the perspective that we took here. There's a asterisk by outsourced on both of these graphs, and you may have noticed this on the previous slide where I had a pie chart showing the applications by supplier. The reason the asterisk is there is because it's really statistically insignificant. There's only 2% of the applications that were designated as completely outsourced in the data set. So that's something that may not be as robust as the other categories in saying, what was the pass-fail rate? And you can see it's like abysmally low. So you kind of have to take that into account. Our second conclusion from the report was that third-party software is a significant percentage of the enterprise software infrastructure, and third-party components are a significant percentage of most applications. Again, pretty obvious on the surface if you think about it. Nobody develops software entirely from scratch. You're always reusing pieces from that other people wrote. You're integrating libraries. If you're writing a web application, you're probably using third-party libraries for logging, file parsing, manipulation, search indexing, and only a very small percentage of the code is something that you actually wrote yourself from scratch. The problem is that most enterprises completely ignore the risk of these third-party components. If they're doing a code review, for example, they only look at the code that they wrote. They're not looking at the other code that is completely tied in with their stuff, right, and is exposed in just the same way. If they're doing a pen test, then okay, those third-party libraries are probably going to be included in the scope, just because you can't easily separate them when you're looking at a live running system. But as far as the SDLC goes, things that you do earlier in the SDLC, whether it's binary analysis or source code analysis or code review, those third-party components are very often overlooked. And people, like I said before, will run business-critical systems on stuff that they've purchased, and they bring into their company without having any idea of how safe it is. So this is not to say that our customers are lying or mislabeling their software as not being third-party. One of the limitations of our platform is that you get to pick, you get one choice basically of where the application came from. So if they kind of identify it as being self or internally developed, then they'll probably pick that option, even though some of it is developed by third parties. We wanted to find out what the actual percentage was of third-party code in these internally developed applications. And we didn't have a good automated way to do that, right? To look at the libraries and say, okay, well, this one's third-party and this one's something that you wrote. So what we did is we took a representative sampling of a handful of those applications, and we basically went through manually and looked at what are the libraries and figured out okay, well, for example, you Google the library and see if you can figure out where it came from. If it's an open source library, if it's a commercial library, then you say it's third party. If if it's full of classes that are com.customer or whatever, then you assume it's custom developed. So it's kind of crude, and unfortunately it's manual, but we want to figure out where that was. And we found that anywhere from 30 to 70% of applications that were so-called labeled as internally developed were actually third-party code. So 30 to 70 is pretty wide, so maybe let's just say on average it's about half. But that's a lot, and people need to start thinking about third-party code as part of the overall risk. Just a quick detour to show you a visualization of the software supply chain for a typical large enterprise. On the left-hand side, you have the development process, the SDLC, and all the different places where code may come from. On the right-hand side, you have the procurement process, anything that you may bring in-house explicitly from an external source. And now everything that's shaded in either orange or gray represents third-party code. Orange is outsourced code, and gray is any other code of unknown security quality, including both commercial and open source code. So if you're not considering the risk introduced by third-party software, you're missing an entire big piece of the attack surface. The third observation from our report was that open source projects have comparable security, faster remediation times, and fewer potential backdoors than commercial or outsourced software. So that's a mouthful. You'll often hear some debates about whether open source software is more or less secure than closed source, and there are religious arguments about this, and both sides have their merits. What we found objectively in our sampling of open source versus commercial software was that they're comparable. Neither one was noticeably better or worse than the other. They were within a few percentage points in terms of pass-fail. One difference we did notice in terms of just the makeup of the things that we detected was that open source software contained fewer items in our potential backdoor category. And that covers a broad spectrum of things like rootkit behavior, time bombs, hard-coded crypto keys, data exfiltration, and things like that. I'm going to stress potential there because it's hard to tell why something, why there might be a keyboard hook in a file, for example, that could be there for legitimate reasons, but it looks like rootkit behavior. So we can't really put our finger on intent there. But we didn't see as much of it in open source. And there could be a number of reasons for that. I mean, in open source, the software is subject to a lot of scrutiny. Everything's public. Somebody checks something in, their name is attached to it, and everybody in the world can see it. In a study that Chris Wysopal, our CTO, and I did on backdoors about 3 years ago, we found that in every public instance of a backdoor we found in open source software, it was usually patched within a number of weeks. So somebody would notice it, and it would work its way out of the tree very quickly and get patched. Whereas we found some examples of backdoors in commercial software that stayed unpatched for 6 or 7 years. The graph here shows remediation times by the different suppliers. So what this is showing you, and this doesn't represent all 1,591 applications, this represents the ones that did not receive an A on their first run through, and on subsequent scans they eventually did reach an A. So anybody who got an A the first time around is not included here, and anybody who has yet to reach an A is not included here. So this just kind of shows the people that have done the process and have gotten from something lower to an A up to an A. But the open source number is significantly lower. They took an average of 36 days to remediate as opposed to 48 for internally developed and 82 for commercial, which is pretty terrible. And we can make some guesses about why that's the case too. In an enterprise environment or in a commercial situation, an ISV, you have probably more political complexity, you have more organizational complexity that are going to prevent fixes from getting shipped or even implemented as quickly. Open source software, all the times, a bug will be reported, somebody will just fix it, check in a fix, and they'll release a point release, maybe a few days later or maybe a week later, depending on what it is. Whereas commercial software may have more rigorous QA testing or acceptance testing before they can release. It's not to say that open source software doesn't have really good QA suites, but again, we're just kind of guessing here about why this is the case. From personal experience, also, I think the commercial space and the enterprise space has kind of a prove it to me culture or an attitude. And we found in dealing with open source companies or open source projects that when we found something that was a flaw, they would look at it kind of for what it is. Like they understood the pattern that we detected and why we detected it. And we may not have showed them exactly what the exploit scenario was and showed them, well, look, here's how somebody might get a shell, because again, we don't do that in static analysis. But they saw why the coding pattern was bad, and they said, oh, yeah, we should probably fix that. And they do. Whereas a lot of times in the enterprise space or with ISVs, there's a lot of back and forth. They say, okay, well, I don't believe that this finding is true. Like, prove it to me. Show me exactly how it can be exploited. And in the time that they could have spent fixing 50 cross-site scripting issues, a minute apiece, they're arguing instead, right? They're debating the merits of the finding rather than just fixing the problems. And that's fairly common. That happened on a couple open source projects, but it was far more prevalent in general in the enterprise space and the commercial space. Finding number 4 was that a significant amount of commercial and open source software is written in C++ or C, which makes it disproportionately susceptible to the types of vulnerabilities that can allow an attacker to take over a system. 42% of all the C and C++ apps contain flaws that, if exploited, could lead to remote code execution, similar to the Aurora attacks on IE6, that sort of defect, like a buffer overflow or integer overflow or use after free, those types of things that are kind of game over vulnerabilities. And there are a lot of mistakes you can make in Java and .NET as well, but because you don't have direct memory manipulation in the majority of cases, you don't have as many of those game over vulnerabilities in those languages. Finding number 5 is that the pervasiveness of easily remedied vulnerabilities suggests a lack of developer education on secure coding. So here we're looking at the overall distribution of all the flaws that we found and kind of asking, why is that the case? Why are there so many flaws in these certain categories? Not surprisingly, maybe, cross-site scripting tops the list. So 33% of all the flaws that we detected across the entire data set were cross-site scripting. Information leakage was also pretty significant, but it's definitely falling quite a bit behind cross-site scripting. And then everything else kind of is way below. CRLF injection, 8%, and then it goes down from there. The reason cross-site scripting is so prevalent is because it can happen anytime a piece of user-controlled data gets printed out to a web page, and that happens all the time. Whereas, for example, SQL injection is also a pretty common mistake. You don't make as many database queries as you do writes to the response. So it kind of makes sense. That's not a new problem. Obviously, cross-site scripting has been recognized as a security problem for well over a decade now. Everybody's aware of it. Everybody's heard of it. Even developers that are not really very experienced in security have probably at least heard of cross-site scripting. But it's as rampant as ever, 33%. There are all these resources available on how to prevent it. OWASP provides libraries on helping eliminate the risk. There's a cheat sheet. There are entire books dedicated to cross-site scripting. Despite all that, it's still at the top of the list. This is another view of all the vulnerabilities that we found, except that it's a different slice. And so what this is saying is that this is showing the percent of applications that are affected by at least one flaw in that category. So for example, the number 1 item on this list is cryptographic issues. 44% of all of the applications included at least one flaw that fell into cryptographic issues. So this is just a different way to look at it. Cross-site scripting is still near the top, right? It's a third of all applications. We've had some questions on that. Why is that so low? Well, part of the reason is because not all the applications we analyze are web applications. Only 60% of the apps in the data set were web apps. So that kind of makes sense, right? The non-web apps won't be vulnerable to that category at all. But all applications are vulnerable to cryptographic issues.